Welcome, my name is Wolfgang Polivke. I'm head of the Thermo-Fluid Dynamics group at the Technical University of Munich. And in this slidecast, I want to talk about the research we are doing, which concentrates on thermoacoustic combustion instabilities. These instabilities can do very serious damage to a combustor. One example is showing on this slide, as you see here. Thermoacoustic instabilities are a fairly exotic phenomenon, but they came into the focus of engineering attention in the 50s and 60s. Here, for example, you see rocket engines on NASA test beds, which suffered very serious damage from thermoacoustic combustion instabilities. But it is not only rocket engines, it can also be household burners, it can be industrial burners, or it can be gas turbines. And this brings us to present-day applications and present-day challenges for research in gas turbines, and that could be stationary gas turbines for power generation or gas turbines for aeronautical applications, for planes, jet planes, so for propulsion. The thermoacoustic instabilities impede the development of reliable and low emission and quiet engines. And what you see again here is a before and after a combustion instability. So what's the physics of this effect? Which interactions, which thermofluid dynamic phenomena can cause such catastrophic damage to a combustor? Well, the phenomenon as such is not terribly new. It was first observed by the Dutch physicist Rayleigh in 1895, and here I'll show you a video that I gleaned from YouTube, from Michigan Technological University, and it shows an electrical Rayleigh tube. I'll start the animation now. Rayleigh himself did not have an electrical tube. He heated his tube with a candle, but the electrical heating has the advantage that it can make for a continuous sound. So what is happening here is, here in the center where you see the glowing spot, there's a little piece of wire. And as you saw, as this thing starts to glow, sound develops, and as you turn off the electricity and the wire cools down, the sound disappears. Now the same thing again. With a simple zoom in on the wires. You see there's nothing fancy happening here. This is not a loudspeaker with magnets and coils and a membrane going back and forth. So what is causing the sound, and why do we call it an instability? Well, fundamentally, you can explain this phenomenon, this instability, as an interaction of fluctuations of pressure and velocity and heat transfer in feedback. And the feedback is important here. On the one hand, you have fluctuations of pressure and velocity in this tube, much like you would have it in an organ tube. And the sketch here on the left illustrates, on the one hand, the velocity vectors. At this snapshot, everything would be flowing towards the center, and as a consequence, the pressure in the center would build up. This is what is indicated by the blue color. So clearly, in a standing acoustic wave, or in any acoustic wave, pressure and velocity talk to each other. There is feedback between these two quantities. With the hot wire, we also have heat transfer. Depending on the flow rate of the gas across the wire, you have more or less transfer of heat from the heated wire to the gas. And then the last statement here on the slide is something that needs a bit more explanation perhaps. Fluctuation of heat transfer is a source of sound. Why is that? Well, think of a loudspeaker. A loudspeaker is basically a box with a membrane. And the membrane, if you send an electrical signal to your speaker box, moves forward and backward, moves out of the box and into the box. increases the overall volume and pushes the surrounding air aside, or decreases the overall volume of the box and therefore sucks in the surrounding air. And this increase and decrease of volume is what is a monopole source of sound. Now, in a stream of gas, heat transfer or heat addition in general is also a source of volume. Why? Well, because the cold stuff has lower specific volume than the hot stuff on the downstream side of the heat source. So a heat source is a source of volume also, and the fluctuating heat source is a fluctuating source of volume, and thus it is much like a speaker box which increases and decreases in its volume. So in the arrangement as shown here, a heat source that responds to velocity, for example, in an acoustic resonator, that gives rise to a feedback coupling between heat release or heat transfer, pressure, and velocity. And these three in combination can go unstable. And this instability criterion is spelled out here on the title line. This vibrations, this instability is encouraged. It is possible if heat be given to the air at the moment of greatest condensation. Now, that's old school English. What it means, heat must be given to the air with the right timing if the pressure at the heat source is highest. This is not obvious, not perhaps totally easy to understand, so I give a simple analogy which perhaps you know. If you take a small child and put it on a swing, and the child has seen the bigger children sitting on the swing and they're throwing their legs back and forth and they're bringing the swing to large oscillation amplitudes. A child will of course try to do the same because that looks like fun, so it'll start swinging its little legs back and forth. But in the beginning, it will not do it in the right way, which is an immense source of frustration. So the child will sit there on the swing, throwing its legs back and forth and be very frustrated and start crying. But eventually it gets the hack. And the trick is, of course, that they have to have the right timing between the movement of the leg and the swinging motion of the child on the swing. Now, as you swing all the way to the back, you have to stretch out your legs. And then as you come, well, you've practiced this yourself. I don't have to explain that to you. So for this type of feedback, timing is all important. And that is what the Rayleigh Criterion is all about. He says heat release, which means volume creation, must coincide to some extent at least with high pressure. And as a matter of fact, there is a thermodynamic analogy here. We all know engineering thermodynamics. Here you see a PV diagram to the left center, pressure and specific volume. And the blue line that you see here would correspond to isentropic compression and expansion that a volume of gas experiences if it is imposed to an acoustic wave. Only an acoustic wave, no heat release for the time being, right? For the blue line, it's only acoustics. Acoustics is isentropic, so you compress the gas, you expand the gas, but nothing interesting is happening. However, what happens if you have not only compression and expansion, but also heat release and heat rejection then? Right? In fluctuation means you have part of the cycle where you have addition of heat, part of the cycle where there is rejection of heat. Now if you look at the red circle, which brings you from 1 to 2 prime to 3 prime to 4 prime, that is a situation, you can trace this out also with the diagrams on the right, where pressure and velocity, so pressure would be the black continuous line here on the top graph, are in phase. So that is, heat is added at the moment of greatest condensation, as Rayleigh would say it. And this corresponds, as you see in the PV diagram, to a thermodynamic cycle with a clockwise sense of orientation. And we know cycles with a clockwise sense of rotation are engines. They generate mechanical energy. And in the case of thermoacoustic, these interactions between fluctuations can generate perturbation energy. And it follows that a little perturbation can get this little thermoacoustic engine going, and it generates more and more acoustic energy, which means that the fluctuations at the heat source become stronger and stronger, which means that the generation becomes stronger and stronger, and this whole thing can go through the roof, develop tremendous atmosphere, and blow up your combustor or your heat release rate. Because, I haven't mentioned this, but I should do this now, of course, a Rayleigh tube is just one example. You can also have a combustor, or well, for the rocket engine, it should be pointing downward. So the same physics, unsteady heat release resulting from acoustic perturbations couples with acoustics, the same physics gives rise to thermoacoustic oscillations also in gas turbines and rocket engines. Now, what we would like to do is, of course, to analyze these phenomena. Not everything is as simple as the Rayleigh tube in its physics, although the Rayleigh tube, if you want to do things with quantitative accuracy, is already quite challenging. But if you have a turbulent flame, for example, in a combustor, and that is what you're seeing here, things become very, very complicated. So we have here a combustor, flow is from left to right. On the left we have air and gaseous fuel coming in. There's a premixture, it goes through a swirl generator. So in this tube which you see on the left hand side, you have spiraling flow from left to right into what is the combustion chamber. That is this thing with the square cross section. And on the bottoms you see a color image of axial velocity, and on the back side you see a color image of heat release rate. This is a turbulent. Also you see these wormy structures which indicate vorticity, vortical structures, and the orange surface indicates areas where burning actually happens in this flame. So you see it's a terribly complicated phenomenon, lots of small-scale activity. You see a pulsating behavior here, which results from the thermoacoustic instability. But on top of this overall pulsating behavior, you also see a lot of small-scale activity, which is a result of the fact that we have a turbulent flow here. Now, do we need all this information? How much information is this anyway? This is from a Large Eddy Simulation, which a doctoral student of mine carried out a couple of years back. And this had some 10 to the 10 degrees of freedom. So it's a fairly expensive simulation, runs for several weeks on our SuperMOOC supercomputer. So this amount of information is expensive to generate. Do we need all this information? As a matter of fact, we don't. For thermoacoustic stability, what is needed predominantly is the response of total heat release to flow fluctuations, to acoustic waves. And acoustic waves are fairly large-scale phenomena, so they don't care very much directly about all the small-scale stuff. So the important thing that we're doing in our studies is try to deduce low-order models with a much smaller number of degrees of freedom from the Large Eddy Simulation. So we try to teach the low-order model, which has a few hundred degrees of freedom, the important aspects of the flame dynamics in a Large Eddy Simulation. And what you see here looks quite complicated. It is something you may have seen in control theory classes, or something you may have seen in signal processing classes. It's a technique called system identification, where you extract low-order models from time series that you generate in experiment, or which you generate, as in our case, from a high-fidelity simulation. Nowadays, you would call this a version of machine learning. System identification, as we've used it here, and as we've used it for a number of years now actually, is a form of supervised machine learning in modern day language. Okay, So what is there any, as I said, thermoacoustic instabilities have been around for some time. Is there anything fundamentally new? And as a matter of fact, there is, and I'm proud to report that recent work in our group really played a crucial role in identifying what is now known as the intrinsic thermoacoustic feedback loop. And that is what I tried to get across with this slide here. Up on top you see a combustor. As indicated previously, air would be from left to right. We have the flame in the center. We have acoustic waves traveling away from the flame. These are the wavy lines. And then they're reflected at the inlet and at the exit. And this was what generates the feedback loop. Now, the established understanding was always that if you kill the feedback, so if you set the reflection at the inlet and the exit at the exit to 0, you would also kill the instability, because without feedback there is no self-exciting mechanism which could amplify small initial perturbations such that they grow to large, possibly disastrous amplitudes. However, it turned out with work at TU Eindhoven in a simple numerical analysis, basically a paper and back of the envelope calculation, surprising result: if you set the reflection coefficients to 0, you still get unstable, the model still predicts instability. And the reason for this was analyzed in our group, and we identified what is called an intrinsic feedback loop, a feedback loop that does not rely on reflection by the resonator, but is a local interaction between the flame and the approach flow. And there is, the sketch here should again remind you of control theory. And as a matter of fact, control theory concepts are tremendously helpful in analyzing thermoacoustic instabilities. But it's a bit too complicated. You can read about it in our papers. I'll give you a simple analogy again, which you should be familiar with. Here you have a microphone and a speaker, and I guess you've all heard acoustic feedback in a PA system, where the hum from the amplifier system is reflected by the concert hall or by the stage environment, reflected back to the microphone, and then through the microphone, through the amplifier. Again, you have a feedback loop that can go unstable and develop these ugly whistling sounds which are deafening to the ear. Now, in addition to this large feedback loop, which involves the environment, the concert hall, for example, there could also be, and in this example that's quite obvious, there could also be a direct feedback loop. If you place the microphone in front of the speaker, you have a direct feedback loop that does not require reflection by the walls of the concert hall, but you can set up a very intense feedback loop directly. And we are exploring the consequences, and there are many of them, and some of them are quite paradoxical, but can be explained with some thinking, that result from the intrinsic thermoacoustic feedback. Is thermoacoustics always bad? No, there are also situations where you can exploit thermoacoustic effects to do something useful. I said in the beginning, hey, you can do a PV diagram, you can interpret the thermoacoustic interactions as you would interpret a heat engine. And as a matter of fact, here you see a little picture of a thermoacoustic heat engine, a device that can be used to convert heat to mechanical energy. And there are also, according similar devices that can have a refrigeration effect. So you can have a thermoacoustic refrigerator without any moving parts. That has some advantages possibly for some applications. And the working principle of such a thermoacoustic heat engine could be explained with a picture as shown here. You consider a volume of gas that is compressed and pushed back and forth by the acoustic wave. And in addition, this volume element of gas is in the vicinity of a wall, and the wall has a temperature gradient. That's what the colors here indicate. So we have a piece of wall. Below the wall you have a volume of gas, and we have 4 snapshots here what is happening to the gas. First we compress it. That's what the standing acoustic wave, in this case traveling acoustic wave does. Then the wave, the acoustic velocity, pushes the compressed element to the right side where the wall is hotter, so there is heat transfer from the hot wall to the volume of gas. Then the pressure decreases and the gas expands a little bit, and then the acoustic pushes it back. And if you put these 4 states on the PV diagram, you will see that this corresponds to our cycle 1, 2 prime, 3 prime, 4 prime on the PV diagram, which means this is a process that can generate mechanical work. Okay, enough for today. This was meant to be a fairly short talk. If you want to know more, visit us on ResearchGate or on our YouTube channel. How do you find the YouTube channel? Well, there are some links to that on our ResearchGate projects and project updates. So thank you for your attention.